question that often shows up, particularly for linear systems, but particularly for linear circuits, is asking a question. Imagine I have a circuit, say like the one I have explained over right here, or just shown right there. And I say I really want to know what is the response for a single sinusoid. So a sinusoid at a particular frequency, maybe I call it particular frequency F1, or it's accordingly sort of equivalent omega 1, right? Remember there's a relationship that frequency and omega are related by 2 pi. And so you ask, well, what's going to happen? Well, it's particularly interesting because a sinusoid effectively is a sum of complex exponentials. So what you would expect is something like sine omega t is a set of complex exponentials. We know the complex exponentials for linear systems, which are derivatives and so forth. Basically, those complex exponentials go through the system. We've seen this with sort of an e to the maybe t over tau kind of things. You may be used to seeing that. It's interesting in these cases. So the interesting thing we find out though is if I have a sinusoidal input at a given frequency and it goes through a linear system, the output will be a sinusoid of the same frequency. Now there could be a change in the amplitude and the phase, but it will be the same sinusoid and no other sinusoid if it's a perfectly linear system. And if it's a nearly linear system, then you can assume that it's basically going to be a sinusoidal output. And that's sort of where those fuzzy terms get really interesting, and you see this in all sorts of different places in engineering. Because nothing is ever perfectly linear, but maybe it's mostly perfectly linear. Depends on the eye of the beholder. So what you're going to see here is that if I put in an input V in sine omega t, and it goes into a linear system defined by h of s, which I can then say, well, if I have a frequency and I'm looking at the steady state response of that frequency. Okay. Now, that doesn't mean that if I put one frequency in and change to another frequency, I'm not going to have a transient between the two, but there's going to be a steady state. Or if I start from no frequency and go to there'll be some transient in between, and we're not talking about that part of the conversation. You can calculate that. That can all be figured out through all sorts of analysis, including Laplace transform techniques. But we're assuming it's reached steady state, and in which case the only part of S that will matter here is going to be the complex parts. And in fact, the only thing that's really going to matter is going to be the omega part that's related to that frequency. Everything else is not going to be relevant here. And so I'm going to have the structure that's going to give me that input times what I get for that transfer function times sine omega t and then the phase of that transfer function. And so I can kind of begin to work with it like that. Now I might be able to say sine of omega t1 goes into a transfer function 1 over tau s. I get v in of 1 over 1 plus j omega tau. And this is the omega 1 of the input frequency. So I can say exactly what it is. Times sine omega t minus tan inverse of omega 1 tau, which is going to be what I'm going to get for the phase. It's a minus because it's in the denominator. So I get a denominator part of it. And then it's just, this is the imaginary part and that's the real part. So that's why you get a very simple response out. There's also this notation that comes out of this, which is called Phasor notation, which some people find very useful, which basically says, well, if I know I've got a single frequency going in, often this is related to circuits that I know that I'm operating primarily around a single frequency, more or less. I will say, well, I have an input at a particular angle, and so it has 0 phase shift, and I'm just going to look at here is what is an amplitude, and then what is the angle. I don't worry about the frequency because I know that it's all operating under one frequency, so I don't need to think about it. So it's a way of saying amplitude and angle or phase. So in this very specific case, is again input in a particular phase. I know the input will have this particular behavior, and it's going to be in the magnitude of this. Okay, so remember there'll be magnitude signs there. And then this tan inverse is that. So it would be whatever the magnitude of this is. And the magnitude of this would be 1 plus omega 1 tau squared. So this phrase, just remember there's this interesting concept with phasors, and the frequency is assumed, and that's kind of how that plays. So I can imagine taking the same circuit, doing Laplace sort of transformation on this. And of course, what I know is this is basically a frequency, is basically a voltage divider. So I know it's going to be the resistance of the parallel combination of those two times of that plus the resistance. That can then be reduced down in this form where my tau is R1 parallel R2 over C. You can imagine this also being a case where if the input was a ground, for a grounded input, it's basically I look at the capacitance and what is the resulting impedance around it. Which in fact, if I look at the one port around it at that point, it's basically R1 parallel R2. Okay, no surprise. This all feels about right. So then my magnitude gives me an R2 over R1 plus R2, and then I get this 1 over square root for expression, and the phase is an inverse tangent. Great. So I can begin to look at this. Now if I look at and then I could say, well, imagine I have an input, which I can also write in a Phasor notation. My output is then going to be input times the magnitude of that quantity times tan inverse, which is basically this whole quantity here. I could go ahead and calculate this for an interesting case. Imagine, I have a 1 volt input sinusoid, again 0 phase. Use these values. My tau is going to be 1 millisecond. As a result of that, I'm going to get this particular magnitude response. And so at 160 kilohertz, which turns out to be 1 kilorad per second, my resulting amplitude is basically 1 half of 1 over square root of 2, and then minus 45 degrees. So I can kind of look at structures like this and in a very nice way sort of simplify out some of the issues and things that I'm seeing here. And so I can always kind of handle these notation and handle things at a particular frequency in a very simple way. And this turns out to be a very, very powerful technique and sometimes a nice way of simplifying some of the analysis we do for some of these larger linear systems.